the schedule a little bit. I had built in an extra day into the schedule I built for, you know, the random who knows whatever could happen kind of deal. And so because we had whoever knows what could happen kind of deal go on, I had it so that you had the option of having the test on the 19th or the 21st before spring break. And so we're just moving the test to the 21st, which actually means it's the very period before we go to spring break. I didn't want to do that, but that's where we're at. So in order to get through the content in a logical time frame that gives us at least a month to review, that's where we're at. So I just wanted, before we go over the objectives, just to show you the schedule revision. The main thing to note is that you're not getting a mini assessment today. So I think you're not getting a mini assessment today. It will be on Tuesday. So your first mini assessment is going to be next week on Tuesday. It's going to be based off of the lessons from Monday, free radical substitution, and the lesson today. So today there's going to be a lot of reactions. They're all the same type, but there's going to be a lot of them. So you can expect that there's going to be a decent amount of material to study still. And as we go through the material, there's going to be more to study as we reach each mini assessment, because the way that I'm going to do them, mini assessment 2 is still going to include the topics that were on mini assessment 1. It's just going to build and build and build as we go through the unit. So you'll see that next week there's 2 mini assessments on the 13th and on the 15th, and those will take place in the last 15 minutes of class after the lesson. So from 2:05 to 2:20. If we finish the lesson before 2:05, then you'll have a little bit of time to review. But they're going to start directly at 2:05 and they'll end at 2:20. That's the time frame for the mini assessment. The week after, I won't be here on that Tuesday, but I told you I created an ed puzzle for that lesson. I will be on next week Thursday giving you the printout, the handout with the lesson notes, and you can watch that at your leisure. Whether you want to watch that beforehand or during the class period, I will leave that to you. But you will take notes on that lesson that I will have recorded, and it will be on ed puzzle. I'm giving you that on Thursday for the week after on Tuesday. I will reteach some of it the next class period along with the mechanisms that go along with those types of reactions on that Thursday. Note, I did not put a mini assessment for that whole week for that reason, because I do want to reteach the topic a little bit and make sure you have full understanding of it before I assess you on the topics including that. So then the week after that, 226, there's 2 mini assessments, one on Monday, one on Wednesday, and then on that day where I've signed at least 4 or 5 of your field trip forms, I'm giving you that ability to go on that trip, the college trip, without fear that you're missing material here. We're setting that as a review day, and I try not to put a mini assessment that day either. So we'll be practicing and reviewing that day. So those of you that are here, we never stop. We will make sure we are understanding the material. We'll use that time to practice reactions more and make sure we're shoring up wherever we've gotten to. The week after that, I found out that the 5th is probably going to be the school day SAT, I believe, the 5th. And so you should be back in this class at some point. And so I'm making sure that that lesson is going to be short on the 5th. And on the 7th, that'll be when you have your mini assessment. So notice I did not put a mini assessment on the day of the SAT. I did that on purpose. So it's going to be on Thursday that week, not Tuesday. So I've thought about it as much as I could. And then the next week, you've got stuff. There is a lab day. I do have a lab built in because one of your qualitative analysis type labs could be with organic chemistry. So there's a lab day on the 15th, and then on the 19th is a full review day, and the 21st is your main exam. Good? Understand the schedule? You miss a day, you miss whatever, you have to catch up on your own at this point. Yes? Here we go. So today, what we're going to do, Unit 6, Part 2. We are leaving alkanes behind because they're boring and nobody cares about them. They're nonpolar. They don't do much. You can burn them, which actually isn't great because if you burn plastics, not a great idea. And we'll learn about that on Tuesday. And you can do free radical substitutions with them, and that's literally all you can do. So they don't really give you much of anything important. So alkenes are much more interesting. And so today what we're going to be going over is something called alkene addition reactions. And we're also going to be learning the second out of 5 mechanisms you've got to memorize. Remember, mechanisms are how the bonds are broken and how the new bonds are formed in the chemical reaction. And I usually like to tell a story to help you remember those. So we'll have a mechanism today in the lesson. So first of all, before we get to the objectives, what's an alkene? So this whole lesson lesson is about this class, this homologous series, this class of molecules. We got a double bond between two carbons. One of the classic things you can do with them is you can break that double bond, that pi bond, and you can add across the double bond, and that's what you're going to see today in today's style of reaction. So let's take a look. These are the objectives. Candidates should be able to describe the reactions of alkenes. The electrophilic, which I haven't taught you what that is yet. What in the world is that? So there's going to be some terminology to go over today. Electrophilic addition of hydrogen and hydrogenation, steam, H2O gas using an H3PO4 catalyst, hydrogen halide at room temperature, halogen X2. That was our first objective. What are the addition reactions that we're going to do? Next, describe the use of bromine water, we call it, to show the presence of a C double bond, C bond. 14.2.4, here it is, mechanism, what does that mean? Describe the mechanism. Show what happens to go from a reactant to product. What exact bonds are broken, what exact bonds are formed. You learned the first type on Monday, we're doing the second type today. And they said using bromine and ethane and hydrogen bromide and propane as prime examples. That doesn't mean those are the only ones they can assess you on, but those are examples that they want us to study. 14.2.5, describe and explain inductive effects. What does that mean? Words. Of alkyl groups on the stability of primary, secondary, and tertiary cations formed during electrophilic addition. This should be used to explain Markovnikov addition. That sounds like reading that, given what you know, you're like, what in the world is any of that? What is that? What does that mean?
All I heard was a Russian guy.
Markovnikov. We'll be learning something called Markovnikov's rule today, and Markovnikov addition. Yes. Yes. Was this too wet? I will give it some now. This is for you. All right, so sounds like a lot. Sounds like a lot of new terminology to learn. So like I said, breathe in, breathe out. Let's get to it. You got your flashcards out and available? All right. I'm going to go back to our flashcards periodically for our project as we go through types of reactions. Remember, for every type of reaction you have, I want you to make 2 or 3 flashcards. The first one should be the name of the reaction in the front and what happens in the back. So I haven't taught that yet, so I'm leaving this blank. We'll come back to this. The second one is the conditions for said type of reaction. What are we specifically supposed to know? For example, in free radical reactions, we know that this only happens if there is UV light. And finally, the last one is going to be an example reaction. So as we go through each one, we're going to do that. We're going to make one that's the reaction type and name, the one that's the conditions required, and the one that's an example reaction. So I'll come back to these to fill them in later. So here we go. Addition reactions. I'm going to discard these notes so that I can go back to the flashcards as we need to. Addition reactions of alkenes. Back in organic part 1, I discussed with you the major types of reactions. We said substitution was one, where a swap happens. We said addition was another. What happens in an addition reaction?
The reactants formed to produce the product.
It looks a lot like something we saw in Prius. What does it look exactly like? I remember Prius. Doesn't it? Where you have 2 reactants going into one product. That's because it is a synthesis. But in organic chemistry, it is specifically called addition if we are adding each atom across the double bond. So you'll notice what happens here is one of the atoms adds to one of the carbons, one of the atoms adds to another one of the carbons, and instead of having a double bond, you have a single bond in order for the octet rules to still be satisfied. So the general type of reaction is basically you break that double bond and you add an atom to each side. So this means that in this addition reaction to alkenes, that whatever you have is going to add 1 to one carbon of the alkene and 1 to the other carbon of the alkene. That's the style of the reaction. Why do we call it electrophilic addition? Well, we'll get to that when we learn what an electrophile is. But let's go back, see if you can make your first flashcard. Electrophilic addition. On the back should be the general style of reaction. We know that we're adding to a double bond, right? So you write in the front of your flashcard, electrophilic addition, and you write on the back what's happening. This is just using a random example, right? And you'll notice that there were two options. They gave you x dash y or x dash x. What's the difference between the two? If I write x dash y or x dash x, what's the difference? What do you think xy represents? Compound. Two different elements. And XX means a diatomic element. So that means that XY could be something like HCl, for example, whereas XX has to be something like BrBr. Do you see the difference? What's the same between XY and XX? What's the same? The way to understand it, it's two atoms or two parts, right? There's the part on the left and the part on the right that's getting added across the double bond. So then what's your product of this general type? If it's XY, what's your product? If you write a double bond in your product, that can't be right. Why?
Because then the XY can't combine.
Carbon make 4 bonds. If you can remember one thing about organic chemistry, carbon can only make 4 bonds. If you give it more than 4 bonds, you just wrong. Something really bad happened. Assume the Cambridge Examiner isn't even going to read that. They're like, they don't understand. So then my products could be, if it's XY, I would still have my 2 hydrogens on each, right? That's not changing. That's still there. So I would still have my 2 hydrogens, but what else would I have now? On one of the carbons I would have X, and on one of the carbons I would have Y. So far so good? Y. And if it's XX, what would the product be?
Same thing, except on both carbons you have X.
The same thing, right? You add the same thing on both carbons. So that's how your flashcards should look for the general reaction. General reaction for electrophilic addition, which is an addition to an alkene. You start with an alkene, and you have 2 atoms, or 2 parts. And 1 part adds to the left side, and 1 part adds to the right side. What we have to go over today are what are the specific reactions we could see of this type. And that's what we're about to see after this. There should be no card-on conditions yet because we haven't looked at the type of reactions and what their specific conditions are. And an example reaction, well, we haven't seen that yet either. We're about to. So, good with the type. What you need to do for the flashcard. I'm going to pause a little while for those who are making their flashcards. I told you during class I was going to give you the time to do it during class so you don't have to go home and do it. This is your project grade for quarter 3. It does go in as the project grade in the grade book. So make sure you're making your flashcards now so you don't have to go home and do it and you don't have to rush. The idea is that you go back and you review these. You should be reviewing your flashcards, I would say, even on a daily basis. Once you are practicing, just to go through and make sure that you know what you're looking at for your different types of reactions. All right. We're not going to do conditions yet. We're not going to do this reaction yet because we have to go to type 1. So first addition reaction. So move forward in your notes to type 1. The first one is called hydrogenation. And what happens with hydrogenation? Well, it's exactly what it says. Hydrogenation. What does this mean we're adding?
Hydrogen.
Adding hydrogen until it's saturated. And so this actually, if you were someone who would study making different food products, when fats are saturated, it's because they have only single bonds. You can turn an unsaturated fat into a saturated fat via this reaction of hydrogenation. So if you eat peanut butter, I know some of you are allergic, but if you do eat peanut butter, go look at your label in the back, and unless you, I actually only eat like peanut butter that is detected organic, so it's only like peanuts and salt are the ingredients. But if you have like just a regular thing of Jif or Peter Pan or whatever, look at the back and see what it says. It's gonna say hydrogenated oil, meaning they took an unsaturated fat and they pumped hydrogens into it to make it saturated. First of all, why would they do that? Why would you turn an alkene into an alkane, for example? To make it less reactive, right? So it can store longer. So the purpose of hydrogenation, at least in food products, is to have it store longer. And so this is a traditional process that's used for that. I just wanted to explain a little bit because all of these reactions is not random. This is things that people actually do. And so if you look, like I said, go to your food, look at your ingredients list. If you have peanut butter, look at the ingredients list and you'll see it there. It'll say hydrogenated oil. And that means that they literally just pumped hydrogens into unsaturated fats to make them saturated. So what's the process? You've got an alkene, you throw some hydrogens in, you have to have a nickel or platinum catalyst and heat, that'd be hot. And what happens is if you have the right conditions, all you're gonna do is add a hydrogen here and a hydrogen here. And that's your product. So this turns an alkene into an alkane, which means we make something reactive into something less reactive. It doesn't really do much. And so yeah, there's reasoning for that. So should you be making flashcards on this type of reaction? Yes. So what would we name the reaction for our first flashcard?
Hydrogenation.
We would name it, instead of electrophilic addition, we would now say hydrogenation. And now what would you do? CCHH plus, what's the other product? I mean the other reactant, H2. And the result is you add hydrogen to each side. So you CH. Two reactants, one product. Yes, addition reaction. Should you also include your catalyst here?
Yes.
Just to practice? It's nickel or what's the other option? Flat. Yes, that's why I'm doing it.
Okay.
I'm rehearsing with you the flashcards you should make. It doesn't matter if it's you. It's up to you. Because electrophilic addition, remember, was a type. Now we're going over specific electrophilic additions. This is a specific. This is a sub underneath that. One of the options for the XX is to be hydrogen. And we actually give that a name. We actually call that hydrogenation. It is still the type of electrophilic addition, but it's a specific reaction. What? Yes. They're going to be all grouped under the same mechanism, so we memorize one mechanism for all of them. And we'll be learning that today. That's why I said today's a dense day, because we're going over all these reactions and also the mechanism behind it. I'm giving you a little bit of time. If you're doing your flashcard, what would your second flashcard be here?
The condition.
The condition. So we would say conditions for hydrogenation. And on the back we would put heat and a specific catalyst. They actually want you to know that the element's platinum or, you don't have to say both. We would say platinum or nickel. You can choose one to memorize.
Oh, you can choose one?
Yeah, you can choose one. So for Cambridge, if you just want to write one, I would suggest nickel. But either is fine. So conditions for, if we were to say hydrogenation, we would say, you can take a picture. And I'm going to move forward to the next one shortly, but I just conditions, this also has an example reaction, so I'm not going to do an example reaction for this one. But conditions. If we say conditions for notified at the blank here, that means for whatever reaction we're doing. For hydrogenation. You could also give a reaction and ask what are the conditions for this for an example reaction. What are the conditions?
Heat and nickel.
Heat and nickel, right? Solid nickel, because it's a metal. So nickel solid. Those are your conditions. And you don't have to do an example because I already wrote an example for hydrogenation on the last slide. So the second one here would be your conditions. Conditions for hydrogenation, heat and nickel. We make a separate flashcard for this. I'm coaching you with how to do this because for each reaction, what you should be doing is writing the type, writing the conditions, and writing an example. Or 2 or 3 of those, depending on what we need to do to memorize it. Yes? You don't have to, just heat and nickel would be fine. Since you've already said it's hydrogenation, you just need to memorize the conditions for that are heat and nickel. You don't have to write the reaction again. Good? Now? Okay. We're moving to the next one. So that's hydrogenation. The next one. Instead of adding H2, we could add steam. What do you mean we could add steam? Water, if you'll recall, breaks into 2 components, and this is what you have to recognize. It breaks into H and OH. So in the idea of what could be X, Y, what is your X and what is your Y?
X is H.
Correct. So X would be H, and Y would be OH, just to be clear on what's happening here. So in this reaction, you've got, again, you're starting with an alkene in all of these. And now, if you've got steam, you've got to remember, it's going to be understood as HNOH. So H goes to 1 carbon, and OH goes to the other carbon. And that's what's being shown to you here in this example. Yes? Somebody? Hold on. Make sure. Nope, the past 2. You're good. Doesn't really happen with the addition of steam. Like, here's your name. Addition of steam. It doesn't have a fancy name. I mean, if you wanted to, you could technically call it hydration. Right? Adding water.
Yeah.
You could call it hydration. I don't see them say that, so like in a Cambridge exam where I will hear them call the other one hydrogenation, which is why I'm not calling it that. I'm just saying it's the addition of steam. So here you've got an example reaction and you've got the type. So this is an example reaction that you can use for your flashcard. And you know, for your second flashcard, you make the conditions. What is the specific condition that Cambridge would like you to know for addition of steam? And specifically, they want you to know that you have to have concentrated phosphoric acid. So that's why I italicized it. I went back in to the standard in the book and I made sure that I gave you the exact correct conditions they're currently looking for, which is concentrated H3PO4. So I'm going to give you some time, pausing, to give you a little bit of time. You can write that example reaction for addition of steam. What you're going to notice is that these all follow the same type. Like one thing adds to one side, one thing adds to the other. It's just what are the different things you could add and what are the conditions for each one. Notice there's a note here. This note was also in the textbook, so I wanted to bring it up. When you're doing this, what are you actually making? Not any alcohol with this example. You're making ethanol. Ethanol is useful for many things. One of the things that could be useful for fuel is what they add in when you go to the gas station and says ethanol. It is also what people that are 21 or over drink. They specifically drink ethanol, not pure ethanol, but a solution of ethanol. At least in the United States, the drinking age is 21. And so the idea here is that you could actually, and some people do use this process to make ethanol, but you shouldn't. because there's byproducts in there and you've got the phosphoric acid in there, and it's not very healthy to make through this manner. And so all the alcohol that's sold to people, like in alcoholic beverages, is sold made by fermentation of glucose to get the alcohol, not through this method. So they don't like sit in labs creating alcohol out of alkene. However, it's technically plausible to be able to do. So we're good? Ready for number 3? Here we go. Addition of hydrogen halides. So this is what we would call HX, where X can be fluorine, chlorine, or bromine. So what would happen if you had a hydrogen halide? So this is an example reaction in skeletal form. I know that's not your favorite as a group. But note what's happening here. These are your 2 carbons of the double bond. Do you agree? These are the 2 carbons. On one side goes your one group, and on one side goes your other. Now you have something interesting going on. If you have, and this is 4 carbons long, if you have 4 carbons like this, and you've got HBr, for example, being added to it, couldn't it be possible that bromine could either go to the first carbon or to the second carbon? Because these 2 atoms are different than each other. Isn't it possible that this bromine could go to the end or it could go to the middle? Like it could add either way? It's possible, right? So this is going to be more complicated, and we're going to have a lot to talk about here. Because you'll notice here that they only give you bromine in the middle as the response, not bromine on the end carbon. And so there's actually a reason for this. First of all, write your example reaction. These are your conditions for the second flashcard. Whatever you have, HCl, HBr, or HI, HF, it has to be concentrated, and this does take place. You don't have to write room temperature. It's just to know that there's no heat needed here. Yes?
You have to write the Moscow.
Markovnikov, you do not need to write that in the flashcard right now. However, this is going to come back later in today's lesson. Markovnikov's rule comes into play if you've got 2 different atoms being added. And the Markovnikov's rule says when 2 possibilities of products are formed, there will be a major product and a minor product. The major product is the one that's mostly made. And this is the one that will give you the least amount, the halogen will be bonded to the carbon with the least amount of hydrogen, which sounds so silly saying that. It'll be better when I explain this to you visually. This is because of something known as the inductive effect. And so we're going to we have several slides later on in this lesson explaining what the heck is going on here. But the idea, just to know for now, is when the atoms that are not the same are being added, the one that's not hydrogen gets added towards the middle of the compound. That's all we know for now. It's going to make more sense once you learn the mechanism. Once you learn the mechanism, you'll understand more or less why it goes the way it goes. This is reaction 3. Reaction 3 is we're adding HX to the double bond. X could be fluorine, chlorine, or bromine. So we call it X, HX. I'm giving you some time. If you're filling in your flashcards, I told you I'd give you some time in class as we went along. So remember, for each reaction, you should have an example. These are all of the type electrophilic additions. So you should have an example of this, and you should also have the conditions. The specific conditions to know is that HX, if they ask you for the conditions, it should be concentrated. You do not have to write a flashcard from a Markovnikov's rule. If you make additional flashcards on your own, that's fine. But for this process, you do not need to make one from Markovnikov's rule. And I haven't fully explained what it's even saying yet. Yes? Yeah, I can get you one. Here you go. I'm moving forward in about 20 seconds to explain what's going on a little bit more. All right, we're moving on. The next thing I want to explain a little bit more is called Markovnikov's rule. So what you're going to see here is just an expansion of what was brought up in the last slide. If you have a situation where your alkene is more than 2 carbons, this means that when you add 2 different atoms, there's a possibility to get 2 different products. In this one, if I have HBr, there's a possibility of getting the hydrogen on the end and the bromine in the middle, or the bromine on the end and the hydrogen in the middle. Those 2 different products would have 2 different names, right? One with the bromine in the middle would be called 2-bromopropane, and one with the bromine on the end would be called 1-bromopropane. It turns out that when these reactions are actually done, about 90% of the mixture is this and only 10% is this. So you get both, but you get way more of one than you get of the other. And so that is why we will call this the major product, the one with the bromine in the middle. And the one with the bromine on the end we call the minor product, meaning it's going to be there. It's going to be in the mixture, but only a small amount will be that. And so that's a great question. Julio says, why? And I can't actually fully answer that to you until I teach you the mechanism, because the mechanism will have the explanation of why that actually happens that way. But for now, what you need to know, and the actual way I think I memorized it when I was first studying organic chemistry was Markovnikov's rule. Markovnikov's rule said that, well, the one that's not hydrogen goes in the middle. That's how I just memorized it when I was initially studying it. I don't remember learning the mechanism back then. Actually, I don't believe when I was learning Organic 1 in university that they taught mechanisms that that semester. So I learned mechanisms starting in, I think, Organic 2. And so you learned them earlier, which is crazy to think that most people learn this at like 19 and 20 years old, and you're what, 15, 16, 17 years old, and you're learning the same information that students would be learning in the university. But, yeah, big brain time, yes. 90% or more, and the other one's 10% or less. Just that's the threshold, pretty much the same major minor. And so where I'm getting with this is Cambridge typically only asks for the major product in these reactions and won't ask for the minor product. However, they can ask why this is the major product and this is the minor product. And I have seen them ask for both before and an understanding of why. And so we'll get more to that when we get to the mechanism. But for now, just memorize whatever is not hydrogen goes more towards the middle, and whatever is hydrogen goes more towards the end. That's the idea. Why? We'll come back to it. Has to do with the mechanism. So far, so good? So, practice question. In the reaction of 3-methyl-1-hexene and HBr, 2 possible products are formed. Write both of them and indicate which is the major and which is the minor. I'm going to ask you, would you like me to do this in skeletal, structural, or displayed form? Did you say displayed? Okay. So, we start with 1, 2, 3, 4, 5. I heard more people say displayed. So, 6 carbons, yes? On carbon 1, we do what?
Double bond.
Double bond. On carbon 3, we do what? Do I really have to display the methyl too? Please tell me no. No. Hey. And you said display, so now I'm going to write out every single one of these. I'm going to breathe in and breathe out. 3-methyl-1-hexene, right? What are we putting this with? HBr. Is this XX or XY? What do you think? XY, right? So, because it's two different atoms. So does it matter which carbon of the double bond the hydrogen adds to and which carbon of the double bond the bromine adds to? It does. Now they tell you to say both possible products. So one product is the hydrogen goes to the end and the bromine goes to the one right there. You can only add to the alkene. It doesn't matter what else is in the molecule. You can only add to the alkene. So the idea is that you would erase this double bond and make it a single bond in your product. So we're going to go H, C, H, single bond. C, H, C. You asked me to display, so it is. It's so much right now. When we do mechanisms, it does make more sense to do display. At least display around the, I'll say, the carbon of interest. Now, what am I adding? I'm adding an H and I'm adding a Br. So I'm going to go just do that in a different color. I'm going to add my hydrogen here and my bromine here for one. And my other product would be what? Switching them up, right? And so these are my two possible products. Hope you all start to like structure a little bit more. All right. So now we're going to do bromine here and hydrogen here. So which one of these is major, the top one or the bottom? The one that puts bromine more towards the middle. So this one's what we're going to call the major, which Cambridge will most of the time only ask for major product. And then the one on the bottom will be the minor product. So you're responsible for knowing major product and minor product. This only happens if you have more than two carbons and if which your two possible answers are not equivalent. So like if I was adding Br2, would there be a major and minor product? There's only one way to add two bromines, a Br and a Br, right? So this only happens if these are not equivalent to each other. If it's XY, not if it's XX. All right, well, we got one more type to look at before we start looking at the mechanism. Addition of halogens, which is actually easier than this because halogens is the same element twice, right? So there's no more Markovnikov rule here. There's only one product you're going to get from an addition of a halogen. Ready? Did you get it? Yes? Okay. Do you need a picture, David? All right. Addition. Do you need a picture to finish, wrap up anything? And remember, I'm going to go more to the explanation of the behind the why in a little bit. We got to do the mechanism first. We got one more type to look at, though. We could add a halogen to an alkene. So this is the last type you should make a flashcard for today. I think it's the last type, right? Yeah. It's the last type we need to make a flashcard for today, called the addition of halogens. And so in this scenario, you've got an alkene. You should have a flashcard for this reaction. And you've got X2, where X stands for a halogen. I heard the question, what does R stand for? R stands for rest of the molecule. So it means no matter how small or how large the molecule is, we can address it. We're only looking around the double bond carbon. That's all that matters. And so this is adding a halogen to an alkene. When I add a halogen to an alkene, there's only one way you can do it. Add a halogen to the carbon on one side of the double bond and add a halogen to the carbon on the other side of the double bond. There's a little bit of good news here. There's no special conditions for you to memorize, so you don't need to make a flashcard on that. So no flashcard necessary, because they won't ask you for that. No special conditions here. However, there is one additional thing that I will ask you to make a flashcard for, because there's a whole thing, if you look ahead in your schedule, we will have to know chemical tests. It's such an important topic. And add it in. It's such an important topic because it can actually show up not only on paper 2 or paper 1, but also on paper 3. Last year it was on paper 3. They did chemical tests, and we'll do a laboratory and we'll do some practice labs with that as well. but they did do chemical tests on the laboratory exam last year. So the chemical test for alkenes is the following. If you add bromine to an alkene and you shake it, the bromine color disappears. Bromine, I think I taught you back in earlier units. Do you remember the color of bromine?
Red. Brown.
Reddish brown. And remember, I remember the brown. Like it makes that bromine brown. That's how you memorize it. Brown. So what actually happens here is this is colorless. Alkenes themselves are colorless. You add bromine. Bromine is brown. When you add bromine to an alkene, if the reaction happens, your answer is a colorless liquid. And so the brown disappears. So the idea of the chemical test, if you have an alkene, you add bromine water and you shake it and it'll react and it'll go from brown to colorless. This is an example of a type of reaction I'm going to show you on the 15th of March when we do that lab with chemical tests. So you'll want to make a flashcard because chemical tests, this is actually, if I were to talk about importance of topics, this can show up on paper 1, it can show up on paper 2, and it can show up on paper 3. It will at least be on one of your papers and possibly be on all 3 of your papers. So this is a topic you've got to know. Chemical tests. All right, I'm giving some time. This is the final type of reaction. We're going to do some practice before we get to the mechanism, just to see what is the style of question you'll be asked here, and what does your mini assessment look like for next class, not today. I'm giving a little bit of time. Yeah. That should go on the flashcard.
Ready?
And then you put the information in the back, which basically could be add bromine to an alkene and the color disappears, right? Add bromine to an alkane, nothing happens. It stays brown. And I'm going to show with the practice questions how that looks. So, I still see a bunch of you writing. I'm pausing for a little bit. Yeah. Yes, ma'am. All right, are we ready to look at practice questions? Here we go. I left this intentionally blank because I'm adding the practice questions now. So, first one. Of course, I don't want to write it out. What's the product here? You complete it. See if you get the product. Yeah? So on a mini assessment, oh, let me put this, right? That'll be there. If that isn't there, there's actually no reaction, right? That happens addition. So the answer here is?
Just like that.
This, right?
It's just like that.
A little shifted end over. Okay, we're good with this first one? All right, let's try another. Do you want me to show something besides skeletal for the next one?
No.
That was a very quick no. I'm being very careful to include my conditions. That's what I will do on the mini assessment. What we got going on? I only want the major product, by the way. Major product only. Yep. What do you think? Propanol, which one? Is it propanol?
Oh.
Or is it propanol? It is propanol. Because the group that's not hydrogen would go to the middle. Propanol. Yes? Because it's non-equivalent. X and Y are not the same as each other. So Markovnikov's rule is in play, is the way we would say it. Because this is more than 2 carbons long. All right, let's try a different format. Let's do structural. Structural for the next one. Let's see. CH. C. Plus HI. I only want the major product.
It's just, I don't know what
That's how it's gonna be on your mini assessment.
CH2,
So what is this? What?
no,
there's
CH3.
no reaction.
Why not?
Catalyst?
Under temperature.
Oh.
No, catalyst. CH3.
It's
CH.
happening. I mean, we don't ever say like concentrated like as a reactant. It's happening.
Yeah, CH.
It's happening.
I.
So it's CH3,
Yeah.
I with a menthol.
CH3, and then you could write the I next to it, or you could write the methyl in the I. It doesn't really matter. You gotta get that I there next to that carbon, and then CH2, CH2, CH3, like that. Yes? Or you could write the I below it. Doesn't matter. Are we okay with that? Yes, this is good. One more. How about let's get spicy a notch?
Okay, it's one of those things. What are those called? Yeah, one of those. It'll be 4, 5, 6.
It's a cyclohexane. I'm a terrible artist. It's a cyclohexane. Great. I did better there. It's a cyclohexane.
What's the honor?
That goes up. What does it make?
Doesn't that just this bond break when it has Lugia?
And they have to go
Will be on,
directly. Ta-da! Now you have a glimpse of what your mini assessment looks like. So if you give the reactants, you need to give the products. Like that.
Yeah, great.
Welcome back. Take a picture. All right, how are you feeling about this so far? Beth? So alkenes, we're adding groups that are either the same atom or two different atoms to an alkene. Now that I have taught you the type of reactions, we're going to do one more practice question, and then we got to talk about that mechanism, right? How does this happen? Structure of C4H8. This is from an old paper too. It's shown. And look, it says draw a functional group isomer. What's a functional group isomer of this?
Like the functional group changes?
Can we change the functional group?
No.
Yeah.
How? Yes.
Oh yeah.
Yes. Perfect. So draw a functional group isomer. Did they say how you have to draw it?
No.
Math, you draw whatever your preferred method is. I'm gonna do this because I don't like drawing, but you could have said CH2, CH2, CH3, or you could have even displayed it if you really felt like it, or you could have put the double bond on the second carbon instead of the first. There's plenty to do here as long as you made it an alkene. Alkene that's still 4 carbons long. That's the requirement. From there, what you want to do. All right. So that's one mark out of the 3. Says, yeah, there's a second part. You got to keep reading. That was the first part. Explain how molecules A and B can be distinguished by chemical tests. We have only learned one at this point. There is one chemical test. Yes, Ben.
Alkenes will lose their color.
Alkenes will lose color, alkanes won't. That's literally that. So B will lose its color, the color of bromine. When it's added. A, when mixed with Br2, will stay brown. Or will not change color, you can say. So you gotta, it's one mark to say that the color is lost with B, and one mark to say that the color remains with A. Yes. Yeah. Are we not in Cambridge International Education? Isn't our curriculum British?
And yet, when you type it in a Google Doc, it says wrong.
I told y'all that when I do ionization, I use S instead of Z. It's taken a few years to get there, but now I do color with U. And I do it on my own papers. When I was doing my master's degree, I will keep writing color with a U. And Microsoft Word would keep telling me it was wrong. What? I was writing like in British, basically, when I was writing my own like master's thesis. They didn't knock me for it. It's not wrong.
I think I had one teacher that knocked me for it, and I got so sad.
You did not.
No, I swear.
What did you write?
I don't remember. It's really color.
But yeah, I've gotten to the point where I'm so used to just doing this that I have not like I didn't even click that I wrote it that way till you said something. All right, ready? Breathe in, breathe out. Time for mechanism. So we now learned what happens, what we're responsible for knowing happens to alkenes. Now we have to know the how and the why. That's what a mechanism addresses. How does this happen? Why does this happen? Right? So beforehand, last class that we had a lesson on Monday, we talked about two types of fission in mechanisms. We talked about homolytic, and we spent all the time talking about homolytic, and I briefly in passing mentioned heterolytic fission. But the thing is actually 4 out of 5 of the mechanisms you have to know all take place with heterolytic fission, and only one of them is homolytic, and it's the free radical reaction. So this is more of the standard what happens in regular bond breaking and regular chemical bond forming. So what would standardly happen is the following, and let's use HF as a prime example. If you want to, you can write all of fluorine's valence electrons. You don't have to, but just to know that things are working out the way they're supposed to. What are all fluorine's valence electrons? 7, right? And one of them's in the bottom. So the reason why I like to use this one as an example is because it's very dramatic in terms of, is there an electronegativity difference between those two atoms?
Yes.
Wouldn't you say so? I would say fluorine is a lot more electronegative than hydrogen. So if this covalent bond breaks, what happens is fluorine takes hold. It gets its own electron back, but it's also like, give me yours as well. And so you end up with a full arrow, right? A full arrow, not a half arrow. It's a full arrow this time. And so what ends up happening is you've got H with a +1 charge. Hydrogen has lost its electron, yes? And fluorine has completely gained the electron. So far, so good? Whenever an atom gains an electron, it obtains a negative charge. Something that I preach in first year chemistry a lot. And whenever an atom loses an electron, it gets a positive charge. So through this process, you need to keep that in mind. If something has a positive charge, what does that mean? It has lost an electron. And so that's something to keep in mind here. So this type of bond breaking is an uneven breaking of the covalent bond. This typically happens when you've got an electronegative atom and one that's not so electronegative. This is what we call normal. What we learned on Monday was abnormal. So this is normal bond breaking. Free radicals aren't normal. This is what's normal, where one element's going to get the electrons and the other one gives them up. It's usually not, they go to unstable states. Because remember, in chemistry, the whole reason why compounds form and everything is cation and then anion as a result. Notice here it says that it could go this way or that way. It just depends on the electronegativities of your atoms. And so I had a little bit more here. It's important to note that this arrow is the movement of 2 electrons specifically. So 2 electrons are going wherever the arrow is saying they're going. So if we see an arrow going towards B, that means both electrons of the bond are actually going to element B, and they're being lost from element A. So you always write the arrow towards where the electrons are supposed to be going. So far, so good? That's called heterolytic bond breaking. There's a couple other terminology terms we gotta learn, terminology things we gotta learn in order to understand the mechanism we're about to do. And so this mechanism that is important because I'm not only bringing up the mechanism, this is gonna be the type of bond breaking and bond forming for 4 different mechanisms. So I'm teaching what you need to know to be successful for 4 different processes that take place. So next thing you need to know. When you have a heterolytic bond break and one atom loses the electrons and the other atom gains the electrons, one of the atoms becomes positive and one of the atoms becomes negative. They actually have a new name that you've got to be responsible for instead of just calling them a cation and then anion. And it's because of what happens in the mechanism why these are called what they're called. And so from henceforth, when you see a positively charged organic reaction, something that's positively charged, you are now to call it an electrophile. Why? What does that word mean? Break it down. Electrophile. Phile in the background. What does that mean? Phile means attracted to, right? So attracted to, and electron would be attracted to what? Electron. Electrons are what charge? So what would be attracted to negatively charged things? Positively charged things. So from now on, positively charged, and in chemistry, remember we don't say things, we say substances. So positively charged substances are now to be known as electrophiles henceforth, because they love electrons. They are lovers of electrons. And that's what electrophile stands for. So electrophile means lover of electrons. So something that's very attracted to negative things itself would be positive. Yes? Attracted to negative. Okay, so then what is a nucleophile? How does that word make sense? Nucleophile. Likes the nucleus. Well, what charge is the nucleus? Right. So something that's attracted to a positive charge would therefore be negatively charged. So a nucleophile is a lover of the nucleus. The nucleus only has protons and neutrons in it, so the nucleus is positively charged. Therefore, something that loves the nucleus would be negatively charged. And so henceforth, when we have reagents that are negatively charged in all of these different types of reactions, we are going to call them nucleophiles. That's going to be their name. So far, so good? Notice here that it also says that an electrophile is an acceptor of a pair of electrons, meaning that something that loves electrons will get electrons in a reaction. Something that loves the nucleus will get rid of its electrons. So a nucleophile that has excess electrons will be getting rid of those electrons as a result. And so that's interesting to note and will be important for your mechanism. I'm going to pause to give you some time to make the little notes that I made here, and we're about to get to the mechanism. Remember, mechanisms, how does this happen? How does the addition reaction even happen? If a mechanism shows up on a Cambridge exam, it can be worth up to 4 or 5 marks on a paper too. Most years, you'll get one of the 5. And so 4 of the 5 follow this idea of heterolytic bond breaking and the idea of nucleophiles and electrophiles. So most years you get something off of this type. Last year they actually got homolytic fission. They got the other type. So before we get to the mechanism, can you identify if each of these would be best called an electrophile or a
Negative, so it takes positive.
nucleophile?
Electrophile.
A. Which one? Nucleophile. Remember, the thing you got to keep in mind here is if something loves the nucleus, looks positive, it itself is negative. And it actually means in the process, what's going to happen is bromine is going to be donating a pair of electrons. So you want to write that out because I know on paper 1 exam, they'll ask you what is a nucleophile. It is actually something that has the ability to donate its electrons. And so I'm going to write that there. It can donate electrons. B, CH3, CH2 plus, electrophile or nucleophile? Electrophile. Fiending for some electrons here. Right? That's not that fine. It's actually not okay. This is not okay. We'll talk about this a little bit more later. What's wrong with this?
Absolutely nothing.
What's wrong with this?
It's just happy.
That's happy? That carbon has 6 electrons. 2, 4, 6.
Wait, what?
2, 4, 6.
Wait, yeah.
Is this okay? This is not okay. Not happy. It's fiending for some electrons. It needs some electrons. All right, CH3COO minus. Electrophile or nucleophile? Nucleophile. And CH3 plus. Electrophile. All right, are we kind of okay with this idea so far? So we understand the terminology. Now let's go back to the objectives. What are we learning about today? Because, until I said that, probably didn't make much sense. Describe the following reactions of alkenes. We are learning about the electrophilic addition. So why is it called an electrophilic addition? You must be adding an electrophile. So you should write that down. The reason, because there's going to be nucleophilic reactions that happen, and there's going to be electrophilic reactions that happen. Electrophilic means the first thing you're adding is going to be an electrophile, meaning something that seeks a negative charge. So I'm just adding that in to say, well, that's what that is. That's what that's talking about. Electrophile means now we know we're adding an electrophile. Now, how does that happen? I'm about to teach you. Okay, so write an equation to show the heterolytic fission of the CCl bond. Include a curly arrow. So before we move on, what would this look like? CCl bond. It says write an equation. How would this bond break? CCl. Who getting the electrons? Carbon or chlorine?
Carbon.
Carbon or
You know,
chlorine?
it's 50-50.
Who getting the electrons?
It has to be
Chlorine.
because it's more like
It's closer to chlorine.
because I guessed. Okay.
So you would do carbon plus and Cl minus. That's how you would show that. It only says to show the bond. It's not actually showing. Oh, it says CCl bond chloromethane. I could show the whole thing, couldn't I? This is chloromethane. So if I want to show the rest, what's the rest now? Because it said chloromethane. This would be H, H, and H. And the chlorine with the negative show all the electrons?
Yes.
No.
But what they do require is you show two. So it's really weird. They require that you show this with that to show the extra two electrons went there, like to the chlorine. But I personally would say I would prefer this. Like, I don't like doing that. Like, that looks more confusing to me. So you're going to see me write all the valence electrons because I like to satisfy the octet rule to make sure what I've done is correct. So Cambridge actually doesn't require that. It won't show up on their mark scheme. But I'm just telling you that I do that. That's amazing. Which one of the following species is likely to act as a nucleophile? Second question. Nucleophile. Which one of these will best be identified as a nucleophile? OH minus. Hydroxide. Which one of the following is likely to act as an electrophile? H in the +1 form. Right? That's the one seeking electrons the most. H2 is quite stable. Does not confuse. All right. So we are now pretty much done with our pieces of the puzzle for the most part. We can now take a look at the mechanism of addition reactions. What happens to the alkene? And so mechanisms, remember, should be memorized. You can make a flashcard for them, or what I suggest and what I'm asking you to do is with each assignment that we have a lesson that has a mechanism, to do an example mechanism at the back that you just keep to study off of. When I studied organic chemistry, I was able to memorize my reactions much better if I knew the mechanism because I knew exactly how things happen. So mechanisms are a very powerful tool. And so the question is, how do these two bromines get added to an alkene in this example? And so these are the steps. You don't have to write anything here because I'm going to start everything from scratch, and I'll tell you where the points are at. And there's actually a couple things missing here. The first step is that in your alkene, the reactive part is the actual double bond. The fact that there are two bonds here instead of one, pi bonds break much easier than sigma bonds. Watch me use that terminology. Pi bonds break much easier. It's terrible writing, but pi bonds break much easier than sigma bonds. So that means that if this bond breaks really easily, this is the reactive site on this molecule. This is the source of where the chemical reaction is going to be able to take place. So what happens in the initial part of this reaction is the following. The two electrons from the double bond reach out. That's why you see a curly arrow here. Remember, these electrons are going to the bromine. So these two electrons go to this bromine. And the other covalent bond breaks here to go to this bromine. Now, I told you there's a part missing. This should have a partial positive charge. And you should fill this in because I'm going to show this when I teach it from scratch. I just picked this up online because I created drawing like on a computer. So I picked up this diagram. Partial positive, partial negative. That's step one. These electrons reach out, grab that bromine, and that bromine gets to go on its own. And so you get this product. You get an intermediate that we actually have a fancy name for that I'm going to talk about in a future slide you'll see, called a carbocation. What do you think carbocation stands for? Go ahead.
A carbon that is with one less electron.
So it's deficient in electrons. Carbon deficient electron that has a fancy name is called a carbocation. Carbon cation. It's also called an intermediate. What that means is this is not the final answer. This is the end of step one of the process, but this ain't stable. It's not stable. I told you something was wrong with this. This carbon is not satisfying the octet rule. This is not going to be your final answer. So it's what we call an intermediate. Then this carbon that's positively charged finds this bromine that's negatively charged, and the bromine hooks into the carbon And that's the way you get both bromines added. Now there's a couple of things I need to bring up. First of all, I mentioned these dipoles, so dipoles on bromine must be shown. But how the heck do we know which of these bromines is positive and which of these bromines is negative? Isn't this non-polar? How does that even have a dipole? Brain. Do you remember something about intermolecular forces? It's got dispersion. It's got a significant amount of electrons. It's actually got 70, 35 times 2. So wouldn't it make sense that for a split second in time, the electrons could be on one side more than they are on the other side? So this right here is dispersion, but you can have a temporary dipole. Did it actually matter which bromine was partially positive and which bromine was partially negative, or could I have actually done it the other way, where this was the positive and that was the negative? It could have been either way, couldn't it have been? It could have either been this is positive and this is negative, or this is positive and this is negative. You choose, your choice. If you're drawing the mechanism, you do what you want. So if I want to, I can say it's that way. This means when I draw my arrows, I gotta draw them to the right spot, right? Because if these are negative electrons, they're going to be seeking something that's positive, if that makes sense. Nucleophiles will always be looking for electrophiles, because negatives are always going to be looking for positives. There's a way, and this goes back to in the beginning of previous chemistry. You didn't take it, I know, but in like the unit 1, I said your idea of knowing how charges work is going to really formulate your basis of understanding how all of chemistry works. And that holds true with this. Positives and negatives attract, that's really the main idea of what goes on with mechanism. Ready to see what goes on? Mechanism, step by step, has to be memorized. And I'll outline where the marks usually are, the 4 or 5 marks after we go through the process. So this one, I'm going to show you. It says draw the complete mechanism from scratch between ethene and chlorine. I prefer doing my mechanisms in display, or at minimum in structural, where I display around the part that the reaction is taking place. So I'm going to go ahead and show this in display. Why would this be best to do it in display? No. Why would it be best to do display when I'm doing a mechanism?
Because then it becomes too complicated to read.
If you're reading skeletal, it's going to be very difficult to know what's lost, what's gained. Like, you're absolutely correct. It's much easier to see everything when you display it. So we're going to write ethene, and we're going to write, what's the other one?
Chlorine.
Chlorine. How does chlorine exist? Cl2. And they expect you to know that, given the way that they've written it here. They are expecting you to know your standard states like the back of your hand. They are like, you know that. That's Cl2, right? I'm going to fill in my valence electrons just because I'm just going to do that. All right, so here's the marks. How does this happen? You've got to understand how this happens. The first thing you should do is create a dipole on your chlorine. So first thing is dipole on either XX or XY, right? You've got to create the dipole. Because chlorine is the same as chlorine, it does not matter which one you choose to be positive or which one you choose to be negative. But if this was HCl, would it matter?
Yes.
Totally. And that's important. So here it doesn't matter, so I'm just going to say positive and negative. Why not? So far, so good? Now you start the mechanism. This ethene has an area that's negative, and that's the double bond. That's where the electrons are at. This bond will also break the easiest. That's what I was telling you. So the first step of the mechanism is to understand that this bond actually just breaks, like it's gone. And these two electrons start seeking somewhere to go. Where do they seek? The chlorine that is positive. So they seek that chlorine. But we got a problem. on the conversation for now. And this right here is the first mark. So dipole on XX and XY and initial curly arrow from alkene to whatever is partially positive, right? To whatever is partially positive. That's going to be your mark 1 on this mechanism. Does that make sense? I have written over where I should write this. So what would be the next thing to do? We got to write our products of this process, right? Which is what we would call our intermediate. So we write our intermediate. And what would our intermediate be? I'm going to give you some time to write this down because I'm going to delete it and rewrite it up here. Initial curly arrow from alkene to partial positive. I'm going to write this again, but I need space to write my product. So mark 1 is dipole. Mark 1, dipole on XX or XY, whatever it is, and initial curly arrow, right? Good?
So the arrow from
the alkene to the halogen. And it has to be the part that's positively charged because these two electrons themselves are negatively
So I don't
charged.
have to draw the arrow from the bond to the other.
You need to include that as well, yes.
Okay.
This has to be included. So initial curly arrows, I guess would be better to say. So that would be your first mark, all of this. Now, what do? We write what we have. These two electrons grab this chlorine. So the way you imagine it is it swings out. And you've got this carbon, you've got this hydrogen, you've got this hydrogen, and these two electrons have now grabbed this chlorine. So far, so good? So this pi bond actually becomes a new sigma bond, a new single bond between this and the chlorine. So far, so good? Now, on the other side, you've got this carbon that's added two hydrogens. But is there anything connected to that carbon? There's only one chlorine added, wasn't there? So the other carbon doesn't have a chlorine. And the other chlorine is over here. So what should we write on this carbon?
Positive
Positive sign.
sign. And then negative sign of the
So
positive
this
forward,
is
right?
now an electrophile we formed here. This has also got a name. It's called an intermediate. Meaning that we can't end here. This is not stable. This is not what ends. But if you pay attention to the signs, you're going to know exactly what happens next. This is an electrophile. It's missing two electrons to be stable. This is negatively charged because it's chlorine with 8 valence electrons, right? Which is Cl minus 1, the traditional way we know it. And can't negatives and positives attract to each other? And so how would we write? So first of all, mark 2, just to be clear, what's mark 2?
Drawing the positive and negative.
The intermediate with the carbocation. I'm just going to write with C+, but that's the carbocation. That's our mark 2 for sure. So where's mark 3 at here? This is
Combining the
usually-
chlorine and the carbon.
And what way should we write the arrow? What do you think? What way should we write the curly arrow?
Oh,
So
from
we
the
go-
chlorine to the carbon.
Correct, because it's actually the same idea as a dative bond from what we learned back earlier in this class. The electrons connect into here, right? These are going into here and forming that bond. That covalent bond is only a result of these two electrons, or whichever two you choose. So then it's like this. It's a donation. Good? So 3 is to show the arrow from Cl minus in this case to the C plus. And then your final thing would be to write the final product, which is C, C, H, H, Cl, Cl, H, H, and this is the process of how this happens. So how the bonds broke, how the bonds were reformed to get this specific product. This is the mechanism of electrophilic addition. Why is it called electrophilic addition again? What was the reason it was called electrophilic addition? We know why it's called addition because we're adding two things, right? So we know it's called addition. But where is that electrophilic word coming from? Is the first thing added is positive. An electrophile. That's why we call it electrophilic and not nucleophilic. And there will be other mechanisms where the first thing added is negative, and we will call them nucleophilic. That's where that part of the name comes from. So far, so good? So this was the simplest example I could give you. Like, the simplest possible example. So how could this get more difficult? Well, remember Markovnikov's rule?
Yeah.
We need to use this to explain that, don't we? So let's revisit the idea of carbocation. When a carbon group is positively charged, here you go. It is officially known as a carbocation. This happens when the carbon is missing electrons. So you see it has 6 instead of 8, so it's going to have a positive charge there. There are different types of carbocations that exist. Remember how there were primary alcohols and secondary alcohols and tertiary alcohols? This is the same thing going on. You can have in a mechanism a primary carbocation, which means that the carbon with the positive charge is only connected to one other carbon. Remember, our groups stand for rest, and it's usually some amount of carbon chain. Could be 1, could be 100. We don't know. One carbon connected. A secondary carbocation has 2 carbons directly connected to the carbon with the positive charge, and a tertiary carbocation has 3. It turns out one of these is more stable than the others. What do you think the order of stability is?
From right to left. I mean, from left to right.
It's actually like this. Most stable, 2, least stable. And the idea is that, just to be careful because it's going to be, I wrote it out clearly on the slide. The more carbons you have surrounding the positive charge, the more this positive charge is shared among the carbons. Instead of one carbon feeling really alone, by itself, unhappy, the carbon can share its pain with the others. That is positively charged. We have a name for this. It's called the inductive effect of these groups of carbons that are around this one. It's a way to understand it is with a little help from your friends, you'll feel better. So if the carbon has carbons surrounding it, it's going to be able to handle the positive charge more than a carbon that's alone. Hydrogens are not very helpful because they're very small atoms. They don't stabilize this very well. So that gives us the order of stability. The carbon that has the most carbons surrounding it will be the most stable. And the one that has the least carbons around it will be the least stable. So if you had a 0 like this, this is actually super unstable. Go ahead, Justin. It's just like another way to notate. Tertiary 3. It's not degrees, it's just how many. So 0 to the 0. A math person would be like, what? 0 to the 0? Yeah. So this just means tertiary. When you see it, 3 with a little circle, 2 with a little circle means secondary, and 1 with a little circle means primary carbocation. And this is the way that they'll be notated. Do you understand that idea, though, that the more groups that are surrounding the carbon that's got the positive charge, because these groups are larger, they can help this carbon handle that positive charge it doesn't want to have? It's still not obeying the octet rule. It's still not okay, but it's less not okay than this one. It does, because these are not very electronegative groups, though. So they're called electron donating groups, so they help donate electrons towards this carbon so it feels more stable, as if it had those electrons. Yes?
So we have carbon.
withdrawing groups. So if you have something like an oxygen next to a carbon, that oxygen is a withdrawing group and it's going to make it feel even worse. Because it's like taking the electrons more away from it. That's not a conversation we need to have right now though. We're just keeping it to this, yes? All right, so before we move to another practice example, see if you can do this. Formula CH3 can represent an anion, a cation, or a free radical. Which version of CH3 is an electrophile? Which version of CH3 is a free radical? And which version of CH3 is a nucleophile? How many electrons would each carbon have in each case? In the electrophile, what do you remember the charge is? In a nucleophile, what would that mean the charge is? What does that mean it's down there? It's got a negative charge. So it's that 2, right? What about free radical? What do we know that a free radical has? A single electron, right? So how many electrons, valence electrons, would the electrophile have? Every bond stands for how many electrons? 2, 4, 6. Free radical has how many?
7.
Odd number, right? Definitely odd
7,
number.
8.
It's 6, 7. And then the nucleophile would have an extra one, right? So 8. So 8. Does that kind of make sense?
Yeah.
So as an electrophile, it's lost an electron. As a nucleophile, it's gained an electron. As a free radical, it's like chilling there with an odd number of electrons, which is abnormal. Now, I've already mentioned this, but the words are here that I said. So you don't have to write it down in your notes because I wrote it here, what you need to memorize. The more groups that are attached to the carbocation, the more stable it will be. This is called the inductive effect, or what I like to call it, a little help from my friends. Share the pain, and everyone, and you'll feel a little bit better at least with your friends. All right, so, or your therapist. Mechanism of electrophilic addition. Here we go. So let's explain Markovnikov's rule. How does this happen? The way that it should happen to get the major product. So we're going to do a second mechanism before we leave. This mechanism is for propene with HCl. So let's go ahead and do it. Propene is what? We should either write displayed or I would say structural. Skeletal doesn't give us a lot of information. So I'm going to do displayed again. And what are we adding to this?
HCl.
HCl plus H and Cl, right? This is it. Rehearse the mechanism. Thank you, Jenny, for your help. Yep, I got it. I'll put it away. Thank you so much. All right. Point 1, what do I got to do?
You have to draw the curly arrow.
Dipoles first, though, right? Is there a choice?
No.
The chlorine's negative, the hydrogen positive.
No choice. Electronegativity reigns supreme. Chlorine gets the negative, hydrogen gets the positive. Also, you can see why this is taught later in the course, where dipoles are taught earlier in the course, because you need that for this. Now what?
You have to make a curly arrow from the out arrow to the positive.
What's it going to take? So the question is, you now have an important decision to make. This is going to go here. That's going to go there. How many marks have we earned so far?
1.
We got our first one. Yay. Yes, Alex. Yeah, you may. Here's where your most important decision is. Does the hydrogen go to the left or does it go to the right? It goes to the left. Why?
Because the chlorine has to be closer to the
So your choice is to make this positively charged or to make this. That's the real choice you have. You make this positively charged or this positively charged. Which carbon handles the positive charge better? The one with just on the end or the one in the middle?
The one in the middle.
The middle. It's got more groups helping to stabilize it. And that is what we call the inductive effect, or the little help for my friends. Where secondary carbocations will be more stable than primary. And so that's why I taught that. That's why I taught it in a specific order. So now this tells us this has to be CH3, like that. And then this bond breaks. We got this going on. We got this going on. And we've got what on the side? This is positive charge. And fluorine is negative. Now that you've got the signs correct, you can now know exactly what happens next. What happens next? What's the logical next step?
You take the chlorine and make an arrow to the carbon.
Right, because negatives are attracted to
Positive.
positives, and electrons make the covalent bond. And guess where that chlorine ends up? It ends up in the middle, not on the end. And this is why this is our major product. To stabilize the carbocation, because that's the most stable form, so that's most likely the one that's going to get made. So it's because of this specific step right here of the mechanism. That's why this ends up being the major. Sometimes you'll still get some, of the minor, because you could have it go either way. It's just less likely because it's less stable. And so the more stable thing will be the thing that forms. Less likely doesn't mean impossible. So this is your major product. All right, I think that was pretty much it. This can wait. So for the end of class, remember that I am asking for you to do a mechanism, and I'm going to give you a sheet to do that with. So did we get this down? Or do you need more time? Yes.
What's the condition?
For which one?
The electrophilic.
It just depends on the type.
Oh, okay.
So each one had its own condition.
Oh.
All right, so real quick, for your insert note slide. All right. Today, you will draw the mechanism for the addition of HBr to but-1e. So that's what you're going to add to your homework. So I'm going to go ahead and get that for you now. The little paper. You could start to work on this or do this before you leave. But this has to be attached to your homework for today's lesson. Here's red and the actual homework paper. Here's red and the actual homework paper. Oh, I should have the second one. Just need one. For the mechanism. This, remember, is for the mechanism and then your regular homework. That gets attached to the back, yes? This mechanism goes with your homework. Vincent? Homework and mechanism? Homework? Oh. And you need to draw that mechanism on a separate page.
I love homework.
This was supposed to be given to you on Wednesday.
I think it should have been given to us on Wednesday.
You should have done this whole,
Yeah, because now we have a test on Tuesday in math. And I was like,
well,
your fault. And your fault.
you can.
How dare you?
Yeah. That's the mechanism. So this is for the mechanism, and then this is the regular. Attach the mechanism to the back. We call this the practice mechanism.
Why?
We need to practice. And we need to have one. Sorry. All right, this is for the mechanism to draw. So you draw your mechanism here, and then you attach it to the back of your homework when you submit it. This is for the mechanism you need to draw, and then that's the one on the screen, and then the homework to go along with it. Alrighty, more. This is for the homework and the mechanism. You submit it with the homework, and you present it. This is for the mechanism, and then I have the homework there.
I'm so happy.
They were automatic.
Good afternoon, Golden Lions. This is Emily,
And this is Devin.
and these are your afternoon announcements.
Attention CIE students, here are a few important reminders. Wear the appropriate school uniform. Your outerwear must be in solid colors red, black, or white only. Class shirts are to be worn only on Fridays. School polos should be worn Monday through Thursday. PE uniforms can be purchased online at ible.com or at the intended location. Wear your student ID badge on your neck at all times. Arrive to school on time at 7:10.
Take a picture if you need to before leaving, so you know what mechanism you're being asked to draw.
There's a discipline plan is in effect for dress code and tardy violations. You may all be hit by